So our next speaker is Dr. Mohamad, who is a senior lecturer in water systems at the University of Exeter. And I think senior lecturer is equivalent to associate professor in other universities.
Yeah,
Something
I
like
like such a professor. That means as professor. Yeah, it's similar to a such professor.
All right, thanks.
But we have a such professor as well.
Okay.
So the heat recovery from wastewater is a very simple system, as you see here. You have the upstream where residential areas are, and this discharged relatively warm wastewater, and then you extract the heat at some point before the treatment plant, wastewater treatment plant. So you extract the heat goes through a heat pump cycle, like Neha was explaining. And so it goes into evaporative and compression cycles. If the inlet is around 8 to 21 degrees, then the outlet would be around 65 degrees Celsius, which is enough to heat your water at home, and that can be used for radiator heating and so on. So the technology is there, but to deploy this technology on a large sewer network, if you recover heat, the problem is you're extracting heat from the wastewater, and that will reduce the temperature of the wastewater, which can cause some problems at the treatment stage. You don't want the temperature of the wastewater going into the treatment be less than 8 degrees Celsius or so. Okay, so the question is, how can you recover as much heat as possible without causing significant reduction in temperature, which will affect the treatment quality? So to do this, go to the next slide. You need to simulate the temperature variation along the pipe profile, and here is an example of this simulation. So the solid black line, that's business as usual, where there's no heat recovery taking place, and then you have the dotted line, for example, that's 20 kilowatt recovered. It's not causing much difference in terms of temperature variation along the sewer line profile. But if we recover 50 kilowatts, like the red dashed line, you will have a significant reduction in temperature. And then after maybe 1 kilometer, you reclaim this heat by extracting heat from the surroundings, which is soil and air. Okay, so that is on one pipe. This simulation was applied on a large sewer network of 3,000 pipes. What it tells you here in the horizontal axis is how much heat recover, the hourly heat recover in megawatt hours. Okay, so the more heat you recover, the less temperature. What you have in the left side is the no, go back. Yeah, is this later or? Yeah, never mind. So what you have here on the left side, that is the temperature of the wastewater going to the treatment plant, and on the right hand side, the temperature of wastewater in the sewer network. Talk about 3,000 pipe sewer network. So the model results show these temperatures as function of the heat being recovered. The more you recover, obviously, the less temperatures. But we set a target to say anything below this dashed line is unacceptable. Anything below 5 degrees in the sewer network or below 9 degrees at the treatment plant is unacceptable because that's too cold. So it will tell you how much heat you can recover, what is the viability of heat recovery at certain flow rates in the sewers and certain month. Okay, so that is for a large sewer network. But what we have realized is you have heat recovery, simulated heat recovery, and this is heat demand. This is measured heat demand in the UK for I think 100 houses. So you have two different peaks. You have a gap of 2 or 3 hours between the peak of heat demand and heat recovery, and ideally you want to recover heat. You want to use the heat recovered during high demand. So this means you need two things. You need to store the heat at some point, and you need to predict the heat demand. And this what drives me to use some machine learning tool to predict heat demand. So so this is the machine learning using MATLAB train BR, which is based in regularization function, and I used some publicly accessed data from the natural grid. That's gas data, assuming most of the gas is heat, used for heat. But the data is for random locations across the UK, so you don't know whether this value is for the south of England or north of Scotland, and there's a big difference in terms of temperatures, maybe 5 degrees or even more. And so that is one of the disadvantages of the data, but it's available for public access, and I had 1 year data. 1 year data, and I trained the model on that basis. This is the training diagram. You have 3 inputs and 1 output. The 3 inputs being day, month, and hour, and the output is how many kilowatt hours is used every hour. Okay. You can see this is the training results, and you got 0.93 or 0.94 for R squared, which is, I think, is quite good for such data where you don't know the location. So I wanted to optimize the number of layers, the hidden layers in this function, and also the number of delayed layers. So I use the range between 1 to 30 hours. So it will use data 30 hours backward to predict the next hour. And the hidden layers also I use between 1 and 30. I've done this surface diagram to see the minimum error. So the performance here is the modeling error. And you get 0.165 error. So the darker the color, the less error. And that what happened between 29 and 30. So using these optimum values, you get this plot here where R squared is also relatively high, I would say. But we have an area here where it's these are outliers, and these need further investigation. So because I got the optimum values at 29 and 30, and my range was 30, so I need to extend the range slightly more, but that is more computational time, which is not a big problem. I can use the high-performance computer at the university. And also, I might develop seasonal models, so one for every month and one for every season, to investigate these outliers and whether they will be reduced or not. It would be interesting to see if I add another parameter, because what I've added so far was just dates and time and the energy. If I add temperature, although I don't like adding more parameters, because the more parameters, the more time you take for computation, and also the less likely you'll be able to find them available. My temperature is an easy parameter to find. But we in the UK, we don't have energy data available for particular locations. They don't say the locations for privacy and health and safety, and as if you know somebody's energy consumption, you would go and kill them somehow. I don't know, but this is the way. So if you guys know any data sources, because this is, heat can apply also to cooling, same principles. And then ideally in the long term, we'll apply a full-scale heat recovery and storage system in a lab environment. Next slide, please. These are the references. The first two is for heat recovery. This one for the neural network training. That's all from me. And thank you very much for listening.
Thank you, Mohamad, for a wonderful talk.
Thank you.
Any questions?
So it is true that we can't find the location-based data for energy consumption. Okay.
Yeah.
But did you train your model to still consider in a way that energy consumption might be still different at different locations? Like, was there any training included in your model?
No, I didn't. This is just the raw data, obviously organized, but there's no way I can know the location. And I think these outliers on the diagram, I think it might be related to what you just mentioned.
Yeah.
So there's no way I can change the model to adapt to that, unfortunately, because it's random.
But it's still a very interesting talk. Good.
Thank you.
Thank you.
Thanks, Neha. Any other question from the audience? One quick question. So in your model, you mentioned that you're going this one, up to 30 layers, and you have about 8,000 something data points. Didn't you find it too small data set to fit such a complex model?
Too large, you mean?
The number of parameters in your model I'm expecting are too large compared to the data that you have.
The number of parameters, 3 inputs, so day, month, and hour, and 1 output. But the data points, yes, is too large. However, you just need a high-performance computer. For 30 layers, I think that took like 5 hours on my MacBook.
Okay.
I'm trying now to do on 100 layers, because I get when the optimum comes close to the limits, you want to extend the limit. So I'm going to extend it to 100, and that's why the battery was running out yesterday. So it's going to take time, but maybe I can use the high performance computer as well.
Sure. Thank you, Mohamad.
Thank you very much.